Happy New Year 2026, and I've got a great problem for you. If we have this relationship that the square root of 5 plus 2 root 6 minus 1 over the square root of 5 plus 2 root 6 is equal to a root 2 plus b root 3, then what must be true about a plus b over 2 raised to the 2026 power? There are a few things we can say about this right off the bat, and the first one is if we're raising something to the 2026th power, there's got to be a trick, right? The answer to this is not like 2.5 raised to the 2026 power, and then our job is to figure out whatever that crazy expression is. This must be really nice, which probably means that a plus b is either 0 or 1. But the second thing I want to do is focus on just the left-hand side of that equation for a second. Is there anything interesting we can say about the square root of 5 plus 2 root 6? Or, of course, its reciprocal, because that's really what we're doing here. We're taking a number, crazy as it seems, and subtracting it by its reciprocal. To try and get at whatever deeper thing may be going on here, let's rationalize this second expression. To rationalize something means if we've got something weird in the denominator, essentially we want to get rid of that weird thing. In this case, that means we would start by multiplying by the square root of 5 minus 2 root 6. Of course, we need to really do this in both the numerator and denominator, and so we're going to have that root 5 minus 2 root 6 in our numerator as well. These pairings are what we call conjugate pairings, though strictly speaking, because of the square root here, these actually aren't conjugates, but they are functionally going to act like conjugates for us. In the numerator, simple enough, we have 1 times something, which of course just always is the something. So the numerator is going to be the square root of 5 minus 2 root 6. Our denominator, on the other hand, is going to be the square root of the 5 plus 2 root 6 times the 5 minus 2 root 6. And this is why we use things that look like conjugate pairs. When we have two things plus each other times two things minus each other, they always simplify nicely. They always simplify specifically as the square of the first thing minus the square of the second thing. That is, in this case, the whole thing is going to work out to the square root of the square of 5, that's the first thing in this case, minus the square of 2 root 6, that's the second thing. Now, 5 squared is easy enough. 5 times 5 makes 25. But we can also square 2 root 6. The 2 part, 2 squared makes 4. And then the root 6 part, root 6 times root 6 is 6. So 2 root 6 squared is really the same thing as 24. And so now I notice, oh, this simplifies quite nicely. 25 minus 24 is 1, and of course the square root of 1 is 1 itself. So in fact, after rationalizing that second fraction, I can see that the whole thing works out to the square root of 5 minus 2 root 6. So going back to that left-hand side, what I'm really interested in is the difference between the square root of 5 plus 2 root 6 and the square root of 5 minus 2 root 6. Now, there's not a super easy way to combine these together because the square root doesn't distribute across subtraction. So I can't say this is something like the square root of 5 plus 2 root 6 minus 5 minus 2 root 6. I can't just ignore the fact that there are two separate square roots here. Now, I'm going to do what might seem like a bit of a strange move here. Again, this is just the left-hand side of our original equation, and I'm going to square it. But I don't want to mess with the right-hand side at all, so what I'll need to remember in a few minutes is I'm going to have to undo this squaring, which means eventually I'm going to take a square root before I return this all to the equation. Furthermore, to square this, I'm going to take advantage of something called the square of a difference. If I imagine that the square root of 5 plus 2 root 6 is my x here, and the square root of 5 minus 2 root 6 is my y, then this factoring pattern says this should be the same thing as the first term squared, so x squared, minus 2 times the product of the two terms, plus the second term squared, so plus y squared. Using the square root of 5 plus 2 root 6, when we square that, it's just going to get rid of the root on the outside. That is, it's just going to leave us with 5 plus 2 root 6. And for that matter, I'm going to jump ahead here to the y squared part. That's just going to cancel out that radical on the outside and leave us with 5 minus 2 root 6 when I square the y part. The only other bit I have to deal with is minus 2 times the product of these two terms. But remember, we've actually multiplied these together already. That's what we did when we were rationalizing a second ago, and what we found when we multiplied them is that they made 1. So minus 2 times the first one times the second one is really the same thing for us as minus 2 times 1. So I'm just going to add on a minus 2 here. You'll notice this simplifies super nicely. We have a 5 plus a 5 minus a 2, which makes 8, and then our 2 root 6 and our minus 2 root 6 just go away. So after squaring that expression, what we actually find it's equal to is 8. Now, if you're a little suspicious about why that works out so nicely, you have a mathematical mind and your thinking is on the right track. What's really going on here is we are exploiting the relationship between a number and its reciprocal. Remember, these two radicals were reciprocals of each other. When we pair reciprocals just right, complicated expressions start looking simple real quick. You see the same phenomenon pop up all over mathematics. When you look at exponential growth, recurrence relations, the golden ratio, we can use these properties to generate all kinds of sequences, like, for example, the Fibonacci sequence. That's one of the reasons I'm so excited that Brilliant.org is sponsoring today's video. Brilliant helps you excel in math and computer science with exactly the kind of interactive problem solving you're watching right now. Not only does Brilliant build fantastic lessons that let you move beyond the formulas, their platform personalizes the learning for you. It starts you at the right level based on your experience and helps you advance at your ideal pace. Brilliant's lessons are carefully designed to surface these sorts of aha moments. To learn for free on Brilliant for a full 30 days, go to brilliant.org/polymathematic. You can also scan the QR code on screen or just click on the link in the description. Brilliant's also given my viewers 20% off an annual premium subscription, which gives you unlimited daily access to everything on Brilliant. I hope you'll check them out. Thank you again to Brilliant for sponsoring today's video. Now, it's almost time to return to the original equation. We just want to remember that to get to this 8 in the first place, we actually squared that whole left-hand side. So to undo that, we're going to take the square root of 8. And so in fact, this expression, root 5 plus 2 root 6 minus root 5 minus 2 root 6, is in fact just the same thing as root 8. Or if we simplify that, 2 root 2. Which means in our original relationship, what we actually have is that 2 root 2 is equal to a root 2 plus b root 3. On one level, you can probably already see the solution here. It feels like the only way for this to work is if a itself is the 2 of the 2 root 2, and then b is 0. And remember, this is exactly one of the things we thought might happen earlier. If a is 2 and b is 0, 2 plus 0 is 2, divided by 2 is 1, and of course 1 to the 2026 power is 1. It is worth noting here, however, that that's actually not the only solution if this is the only information we're given. You might recognize something like a number equals one unknown quantity times a certain weight plus another unknown quantity times another weight is a linear equation. There are, in fact, infinitely many solutions for a and b here, and similarly, infinitely many values for the original expression. But what we can show is this solution where a is 2 and b is 0 is the only possible solution in the integers. The way we show it is, I think, pretty cool. If we have this connection, 2 root 2 equals a root 2 plus b root 3, we can start by getting the root 2 stuff onto the same side of the equation, which gives us 2 root 2 minus a root 2 equals, and of course on the other side we just have the b root 3, and then we can divide by root 2 on both sides of this equation. So what we get is just 2 minus a on the left-hand side, and if we do a little bit more of that rationalizing like we were earlier, we get b root 6 over 2 on the right-hand side. Furthermore, if we multiply by 2 over b on both sides right now, we get all the nice numbers on the left, 2 times 2 minus a over b, and then the only thing we leave on the right is the square root of 6. Now remember, we were interested in nice solutions. We were trying to show that a is 2 and b is 0 are the only integer solutions for a and b. This relation is what gives that to us. If a is an integer and b is an integer, then 2 times the quantity 2 minus a over b is a rational number. That's what rational numbers are. They're ratios between integers. But root 6 very much is not a rational number. I can't fit the proof in here, but there is a proof for root 6, much like the proof for root 2, that shows root 6 cannot possibly be any rational number. So as long as a and b are both integers, this cannot possibly be a true statement. With the one exception being that before we did the rearranging and the division, it could be true right now that both sides of this equation are 0. And in fact, the only place they are 0 is where a is 2 and b is itself 0. And so there you have it. Happy New Year. If a and b are integers, given this crazy looking relation, then a plus b over 2 raised to the 2026 power must be 1. There are, I think, some other avenues for interesting exploration here. For example, why is it that 5 plus 2 root 6 and 5 minus 2 root 6 are reciprocals? Are there other numbers like that that we could come up with where, I don't know, 7 plus 4 root 3 and 7 minus 4 root 3 are reciprocals? And then we could use that to build similar problems. As we try to come up with different examples that fit this pattern, can we state what's going on in this problem in an even more general way? I look forward to seeing what you do in the comments. Thank you for watching. Comment down below with whatever I got wrong and whatever I missed. I'm looking forward to seeing comments about root 2 plus root 3, and otherwise I will see you all next time.